Hi, this is Mike Mulholland, and today we're going to look at side-side angle as a potential congruency rule for triangles. So we're going to look at this, and overall, it's not one of the congruence rules for triangles, but there are conditions under which it does guarantee congruence, including hypotenuse-side, and we're going to look at how that works. And this is a sequel to my video answer to explain triangle congruence rules. Near the end of that video, we showed this illustration of two fixed sides and one fixed angle adjacent to only one of those sides, resulting in two different triangles. The red sides are the fixed sides, and the angle with the red dot is the fixed angle. And in that video, we came to these conclusions. The two fixed angles define the shape, but in this case, we only have one fixed angle. Adding two fixed sides is not enough to reliably define the shape when only one of the fixed sides is adjacent to the fixed angle. And either fixed side would be sufficient to define the size of the triangle if it had only one shape, but you can have two different shapes. And so this does not reliably produce congruent triangles, so it's not included in the rules of congruency for triangles. But we're going to explore this further because there's some interesting things about this. So we're going to use some geometry, standard geometry symbols we didn't need in the video before that you probably know. The line over the top means it's that line segment xy. Without the line, it means the length of xy. Angle xyz, that symbol there, and y is the vertex, and the m in front means the measure of that angle. So typically lists and illustrations of congruence rules for triangles include something like the two end result shapes above, and say that thus you cannot use side-side angle to prove congruence. They often include a diagram like the one I'm about to show you to show why there's two possible shapes. And this one continues the color scheme for fixed and unfixed sides and angles that I used before, where red is fixed and black is unfixed. So here we have one triangle, the other triangle. And the reason this happens, leg AB here, the fixed side that's not next to the fixed angle, this angle is not determined, but the length is specified. So this arc here shows various places that would satisfy the requirement of this is the length of AB. Leg AC there's a fixed angle here, so we can't move this line. So the points that work for both have to lie on the arc and on the line. And so here and here work, the only points that work. And that's how we get two possible triangles out of it. And this is just explaining what I just said. And side-side angle explanations usually go no further, but it turns out that triangles with equal values of side-side angle will always be congruent when certain additional requirements are met. And so we're going to try to figure out what those requirements are. Usually not explored or even mentioned because they split side-side angle up into subcases based on additional information that you often won't be given or won't be able to prove. And they're more complicated than what we've considered so far, but I still think it's interesting, and so I hope you will too. So we're going to look at those, and we're going to explore first varying the relative lengths of the two fixed sides, which you do by varying the length of one and holding the length of the other one constant. And then we'll explore the effects of varying the fixed angle. So here we're going to vary the length of the fixed side that's not adjacent to the fixed angle. And the diagram shows doing this, where the angle here is less than 90 degrees. And so first, let's start with considering that the length of that first fixed side, not next to the fixed angle, is the green scenario here. That's like what we've seen. We can get this triangle, or we can get that triangle. Now, what happens if we start shortening the length of that fixed side? In the yellow scenario, it's somewhat shorter, and so these 2 points are closer together than in the green scenario. And the triangles are starting to look a little bit more alike. But if you carry that to its logical extreme, you reach a point where this side is as short as it can possibly be. And that happens when this arc is tangent to this line, touches it in only one spot, the spot where we have vertex A. And so, and if this got any shorter, you wouldn't have a triangle at all because this wouldn't reach this line. So what happens here? Now there's only one triangle possible. So is this a new rule or a new subcase that we can make a rule out of? Not really, because now we have another angle. So we really know two angles and two sides. And so we can do something with that with the rules that we already know. And so what we can do, rule we can use is angle, angle, side. We can go angle, angle, side, or we can go angle, angle, side. So we don't need to invoke anything new in this case. We just need to recognize that when we reach this point, a different rule applies. An accepted rule that's different applies. Now, what happens if we go in the opposite direction? If we make the sides longer and longer. So let's start with the yellow, let's say. So we know what happens there. Now we make the sides longer. The two possible vertices here get further apart. Vertices get further apart. So we've got that triangle or that triangle. But if we make it long enough, what if we make this side the same length as this side? Then what happens? Well, this still works. But this side would be right on top of the other side. Vertex C and vertex A would be in the same place if we go to this side. And that doesn't work. So when they're the same length, you can only have one possible triangle. And if you make this fixed side even longer than this fixed side, again, this works, but this vertex would be down here. It doesn't work. So we've seen that when the first fixed side, the one not adjacent to the fixed angle, is longer than the other one, only one triangle is possible, and then congruence is assured. And this is just writing out what I've been saying. So now what happens when we vary the angle? So for each of these cases here, I've shown the shortest possible length. And we talked about that before, but what's significant about it is that it bisects the possibilities. So that, for example, with this one, if we had that, we could also have that, and this would be right in the middle between this scenario and this scenario. And the same with the green, and the same with the blue. This would be right halfway between that scenario that works and that scenario that works. But see what's happening here? We're getting more and more crowded with less and less room for something to be feasible to this side of this dashed line. And when we get to a right angle here, then the bisector is right here. And so nothing is possible to this side of the bisector, only this side. So when we get to 90 degrees, we can conclude that we're only going to have one possible triangle. And let's take another look at that. With a different diagram. So this works here, not going to work there. What's going on here is these vertices really could be anywhere along these lines. It's just determined by the length of the first fixed side, the one that's not adjacent to the fixed angle. So whatever this length is, we figure out where it would hit this, and then that's our triangle right there. Or same idea here, if that's the length, figure out where it would hit here, and that's our triangle. Only one triangle possible. So how can we kind of, another way of showing that this has to be the case? It seems obvious that in these circumstances, AB has to be longer than BC, but how can we prove it? At a glance here, you can see that these are legs of a right triangle, and that's the hypotenuse. The hypotenuse is always the longest side. But we can come up with a better solution than that, because there's a solution that works for both 90 degrees and more than 90 degrees, the orange scenario here. And that is that when this angle is 90 degrees or more, it's guaranteed to be the largest angle in the triangle of the three interior angles of the triangle. Even if it's 90, the other two add up to 90. Even if it's 1 and 89, 90 is still bigger than either of the other two. And it's a property of triangles that the side opposite the biggest angle is the longest. So that proves that when this angle is greater than or equal to 90, that this side opposite this angle is the longest side, and therefore this side is longer than that side, and we've already shown that that means that there's only one possible triangle. So under those circumstances, this rule, with that additional requirement, then this rule works for establishing congruency. So this ties in nicely with what we talked about before when the angle was less than 90, when you could have this side longer than that side, and then there'd only be one triangle possible. The difference is that when the angle is greater than or equal to 90, it's not just possible, it's that this is automatically true when the angle is greater than or equal to 90. So to summarize what we found out, we came up with two subcases of angle-angle side for which congruence is assured, namely side-side angle where the side not adjacent to the angle is as long or longer than the side that is adjacent to the angle, or side-side angle where the angle is greater than or equal to 90 degrees. When the second subcase applies here, this one is also automatically true, and this one is really the mechanism that drives it. This just forces this to be true. One thing to watch out for that's just a reminder that's just true in all over geometry really is if you look at look at one which fixed side is longer and one looks longer than the other, or whether the angle, how it compares to 90 degrees, whether it's 90 or more or less, based on how it looks, that's not a good idea. It can give you a useful hint, but you should not rely on it, because the diagram may not be accurate, and it may not be accurate on purpose to kind of force you to realize that No, don't trust that. You got to prove it. Okay, the two subcases that we talked about are rarely considered, but a subcase of the second subcase commonly is, and that's hypotenuse-leg. Because right angles are special, it's more likely that you would be told or able to infer that the angle is 90 degrees than any other interior angle. And so, side-side angle or angle equal 90 degrees is often included with an easier name, hypotenuse-leg. So how does, this was mentioned way back at the beginning of the first video. We're finally getting to this rule. And how does it work? Well, hypotenuse and leg tell you it's a right triangle because those terms only apply to right triangles. And the angles equals 90 degrees is implied by those names. We know from the name for the rule that there's this fixed angle, and we know the measure of the angle without including angle in the name for the rule. And by definition, the hypotenuse is always opposite the right angle, and the leg is always adjacent to the right angle. So we also don't need angle in the name for the rule to show where the fixed angle is in the triangle relative to the fixed sides. So hypotenuse-leg is just an easier name for what you might have called side-side angle where angle equals 90 degrees or side-side right angle. It's just an easy way to say it. So this rule, A, is really a subcase of side-side angle, and also its name. This is easier, but these other possible names show you that it really involves sides and angles, and it's not that different from the other rules where the name specifically uses the word side and angle. And thank you for watching. I hope you found it interesting.